we are discussing how a computer executes a program. When I say that a computer executes a program, it's essentially the central processing unit which is executing the program. The program is in the main memory. We have seen how the program execution is performed in the case of a sequential flow of control. We were discussing that where a jump instructions is involved, that means a branching is involved, how the program is executed. Okay, let us examine that program from where we had left in the previous lecture. We said this is a program, high level language, typical high level language program that we had taken. This is the assembly language code, as we are saying. Okay, as I've already explained that this does the job of checking A greater than equal to B or not. The flags are set. Depending upon the flag, that jump negative takes place or does not take place. This portion executes this instruction and then take a jump over to label 2. This portion is an assembly language code corresponding to this statement, and in either case, this portion is assembly language code of this statement which is executed. Okay. Now, crucial to taking a jump, that means whether this portion will be executed or not, depends upon what is the content of these flags. Therefore, in the CPU, central processing unit, associated with the arithmetic and logic unit, always there are few flags, okay, right? Say sign flag and Z flag, we have already discussed. The other flags we will talk about when the situation arises, okay. Now, for whenever arithmetic operation is done, the corresponding flags are set. Now, here we have shown the corresponding machine language program of this assembly language code. Okay. Now, you see this machine language program, I have assumed that once more it has started from the location 0300. Load accumulator A is, the instruction is that opcode for the load accumulator is 03. Address of A is A as if A050. Okay, that means the value of A was stored in the location A050. The symbolic address A is essentially the memory address A050. Similarly, subtract memory, I am assuming that opcode is 0A and the address of B is A052. Now, this typical addressing mode, that means where I am saying the address of the memory location is called a direct addressing. There can be many other kind of addressing, okay. That means many other way that the address of an operand of an instruction can be specified. We will talk about these addressing modes in a later lecture. Now, that way, say here I have assumed that the jump negative, that means if the sign flag is set, then it will jump to the location 0315. Otherwise, it will execute the next instruction. Okay. Now, see 0315, you see 0315 is the instruction for the load accumulator Y. Now, let us see how this instruction, this sequencing of instruction will be done. Okay. Now, the program counter to start with will be pointing here. This is a load accumulator instruction which will be executed, then it will come over here. This is subtract memory instruction, subtract memory B, it will be executed, okay, and the flags will be set. By the time that subtract memory B is executed, this instruction is executed, program counter is now automatically pointing to this memory location, which means the program counter is now pointing to 0306 memory location. Now, If the result is non-negative, then whatever the program counter now is pointing to, okay, this said the jump negative to label 1. Now this instruction will now be executed. Now as this instruction is executed, that means jump negative opcode is taken, then the operand of this opcode, which is the address basically 0315, is now taken, and this 0315 say have been taken into one internal register, some internal register of the central processing unit. That means there will be some internal register, it may be the data register itself, that 0315 will be kept, or it can be kept in some other register, internal register. Okay. Now, as this instruction has been executed, that means jump on negative on label 1, that means fetched and being decoded, the program counter is fetched and decoded. Let me repeat once more, that when the jump negative label 1 instruction has been completely fetched and decoded, the program counter is now pointing to this location. Now, depending upon whether the flag is set or not, okay, that means sign flag is set or not, either this instruction will be executed or it will go to 0315 location to execute that load accumulator Y instruction. Okay. Therefore, at this point, the execution of jump negative instruction will decide, check the sign bit, and will decide whether this the next instructions will be taken for the program counter as it is being pointed to, or the program counter will be loaded with this value which has already been fetched, right? Depending upon the sign bit, which means that if the sign bit is 1, then the program counter will be loaded with 0315, which has already been fetched into the central processing unit. But if the sign bit is 0, that means it is the result is non-negative, then program counter already is now containing 0309, and that instruction will be executed. That way the branch instruction, okay, branch instruction is executed. That means on condition that on which the branch has to be taken place, if the condition exists, then the program counter is loaded with the target of the branch instruction. Otherwise, the program counter, whatever content of the program counter is there after the instruction, that jump instruction, when conditional jump instruction has been taken, okay, the execution starts from that location onwards. Essentially, therefore, any conditional jump is a two-way branch. Either it continues sequentially or it takes a branch on condition being true. Now here another jump instruction is there, and that is an unconditional jump, which means that at the end of that fetch and decode of this instruction, though the program counter will be pointing to location 0315, it will be superseded by the address 031E, which has already been fetched, which means the program counter is pointing to 0315, but it will be loaded by 031E. And as I say, that at the beginning of any instruction cycle, the program counter's content gives the address of the next instruction that is executed. Since program counter will be now pointing to 031E, the instruction execution will start from this location. That means it will start from the location, from the instructions load accumulator. Okay, that way and once it has taken a jump, the program counter will automatically get incremented as every instruction is executed, and the control flow will be sequential. Therefore, the essence of whatever I discussed till now, and that is important for understanding of how a program is executed, is this, that the program consisting of machine language instructions are executed sequentially until and unless there is some condition or an unconditional jump takes place. If it's an unconditional jump, program counter is loaded with the target of the jump instruction, and if it's a conditional jump, the program counter will be loaded with the target of that jump instruction, provided the condition is satisfied. And whether the condition is satisfied or not, that depends upon the previous instructions. It may be arithmetic, it may be other kind of instructions as well. Okay. Now, that's how the central processing unit executes a program, which is a key feature, okay, of a stored programs concept, right? The program is stored, the data is stored, and the control is sequenced through the program as is needed, okay, as is governed by the instructions themselves. Now, we had been talking so long about a, so to say, single address machine. In the single address machine, as I say, that at most one address of an operand you can specify. By at most, I mean there may not be, in some instructions, there may not be any operand at all. Okay, but naturally, that and also that our example machine has only one register on which the arithmetic and logical operations can be done, and that is that accumulator. Only one register are there, but naturally the situations are not like that. There may be two operand or two address machines, there may be three address machines also. Okay, in the case of a two address machine, right, the instructions may be of the form, just as an example I'm saying, say add, then you say operand 1, okay, and say operand 2, operand 1 and operand 2. This we generally call to be source, and this we call to be destination. Therefore, in the case of a two address machine, there are at most two operands, operand 1 and operand 2. Say if I say add operand 1, operand 2, that means content as given by operand 1, okay, the value as given by operand 1 will be added with that value as given by operand 2, and the result will be in operand 2, and that is why we call sometimes this to be a destination. Okay, once more I say that this is a typical example. Okay, it's not of a particular machine that I'm talking of. In the case of a two address machine, this is the way generally, okay, we can write an instruction, right? Similarly, we can say, for example, say subtract, once more say operand 2, operand 1, that means operand 1, 2 will be subtracted, say, from operand 1, and the result will be in that operand 2. Okay, therefore, this where is the result comes to. Now, that is the two address machine. But once more, in the case of a two address machine, that is the maximum number of operand that we can give in instructions is 2. But the number of operand can be 1, or the number of operand can be 0 also. Okay. Now, there can be similarly that, sorry, 3 address machine. In the case of a 3 address machine, as you can very well guess that there will be 3 operands. Say, for example, if I say add, then we can give 3 addresses, say operand 1, okay, or you can specify 3 operands. I should not say that addresses of 3 operands only. We can specify 3 operands, operand 1, operand 2, and say operand 3. This means that I'll take that content of operand 1, or the value as given by operand 1, will take the value as given by operand 2, will add them, and the result will come into operand 3. Once more, this is a typical example. Naturally, it will vary from machine to machine, but important thing is that in the case of a 3 address machine, that we speak of one operand as a source, right? Another operand is the second source, and the third operand as a destination of the result. Okay. And once more, in the case of a 3-address machine, the maximum number of addresses, okay, or the maximum number of operands that we can specify in an instruction is 3. Okay. It can be 2, it can be 1 also, as we'll come to examples later on, right? Now, you see that we had been, in the case of a single operand instruction, this is the instruction cycle I have shown. Only one operand at most we can get that operand address, I say, fetch the operand, right? But naturally, in the case of a 2-address machine or 3-address machine, okay, 2 operand machines or 3 operand machines, the instruction cycle should be modified. Another important point is that whenever we are talking about an instruction, the instruction and one instruction consists of 2 parts mainly, okay? As I said, that one is that opcode part, right? Another is basically the address, or you can say operand part, right? Now, depending upon the machines, naturally that opcode will vary. The instructions or the operations the computer can perform depends upon what are exact the operand codes, okay, that are there. That means what is the instruction set is. That instruction set will consist of different instructions and therefore the different opcodes, okay, and that a particular machine, what that particular machine can do, that depends upon what is this instruction set is. Okay, therefore, that instruction set of a particular machine defines the opcodes of that machine for doing several different instructions. Similarly, that address or the operand part, either it's a single address or a 2-address or 3-address, okay, how you can specify a particular operand is called that addressing mode. Okay, therefore, this gives us the addressing modes that specifies how you are specifying the operand. It may not be the direct address that as I gave an example of. It may be in different ways this addressing of a particular operand can be specified, and a machine, the way that a machine specifies its address of the operand or the operand itself is called the addressing mode. Now, for the instruction set a machine performs and the addressing modes by which it specifies the operand is a very important characteristic of a machine, and a detailed discussion of it we will have in the later course of lecture. Now, just to give a glimpse of that how a instruction cycle may turn out to be in the case of where the number of operands is more than 1, I am showing a typical instruction cycle state diagram. Here you see that instruction fetch has taken place, right? Then it comes to the top code decoding. Then here is an operand address calculation depending upon the the addressing modes that you utilize, okay, or you use, a system use, that operand address calculation is done. Then the operand is fetched, okay. This indirection means also the way that we can specify a particular operand. Therefore, this specifies that how the operand is fetched. Operand address is calculated and then operand is fetched, right? And if it is a 2-address machine and 2 operands are needed, then it will be executed twice. If 3 address machine and 3 operands are needed, then it will be executed thrice. Okay. After that operands, all operands have been fetched, it comes to the data operation. That means the computation is done. Then operand address calculation may be done once more, okay, to store the result. And if it's an indirection, this address calculation goes on more than one step. Then this operand is stored, and at that end of this operand is stored, okay, the CPU sees, okay, the central processing unit sees whether anybody outside the central processing unit, okay, wants the attention of the central processing unit or not. This we call interrupt, and therefore the CPU checks that interrupt here. If there is an interrupt, the CPU processes that interrupt and goes to the next instruction address once more. Now, regarding this interrupt once more, that interrupt may come from the different I/O devices that is connected to the CPU, or it can be coming from, say, power failure interrupts, etc. A detailed discussions of the interrupt handling and interrupt checking also will be having in due course of our lecture, right? Only one thing that I would mention, that instruction here I am showing this just to impress upon that instruction cycle may be quite complicated and quite elongated, right? And there is one thing that is involved, which we call that interrupt check and interrupt processing at the end of every instruction cycle. If that interrupt exists, okay, only then the interrupt processing takes place. Otherwise, it goes to that instruction address calculation for the next instruction fetch once more. Now, one thing from whatever we discussed till now, okay, one thing is very clear, that to execute a program, that there has to be reading from the memory and writing from the memory. In the case of a instructions execution at the fetch, instruction fetch state, an instruction is fetched. Otherwise, an operand address may be fetched, an operand may be fetched, okay, or a result may be stored into the memory, right? Therefore, as I said, that there exists a bus between the central processing unit and the memory unit, that I have a little bit elaborated by means of a diagram here. Here is the central processing unit, okay. Only the registers that are relevant here I have shown. Here is a program counter I have shown of the central processing unit. You see here is an address buffer. This is the data buffer. And one important thing we call the timing and control, which is basically generated by the control unit of the central processing unit, and very important part of a subsystem of a CPU, okay, that generates the control and timing signals, which in fact controls every operations in the CPU, and which controls any transaction that takes place between the central processing unit and the memory unit. Okay. For example, as I was saying, that when I'm fetching a instruction, that program counter content is sent to the address buffer. That address bus, the total bus is divided into 3. Okay, you call that address bus, data bus, and the control bus, which we showed as a single bus in our previous, when I was explaining the execution of a program, right? The address bus contains the address of the memory location from where or to where the content or the data is taken or put into. The data bus contains the data that I am wanting to transfer between the CPU and the memory, and the timing and control tells me how exactly the operation has to be done. Just to give an example, say in the case of operation instruction fetch state, the program counter content is transferred to the address buffer. Then it is thrown, the address goes thrown into the address bus. CPU says through memory read this control line that it wants to read the content of a memory location. The memory unit then takes the address takes the content of that memory location, put into that memory location the data bus, and through this data ready says to the CPU the data is ready, and then the CPU reads the data into its data buffer. By that, what I intend to mean is that there is a protocol and handshaking between the central processing unit and the memory unit, right? In the case of say when the CPU wants to read something from that memory, whether it is an instruction or whether it's a data, the steps that is taken place is this. That the CPU puts the address on the address bus, asserts memory read on the control bus. On getting this, memory module puts the data or the instruction, whatever it is, on the data bus, then asserts data ready, and CPU reads the data. Okay, the 5 steps, the protocol. In 5 steps of this protocol, the memory read is taken place. Right. Coming to the diagram once more, say CPU puts the address, says that memory read, memory puts the data, says the data ready, and the CPU reads the data from the data bus. Naturally, in the case of a memory write, okay, whether it may be writing something into some memory location, CPU will put the data, CPU will put the address on the address bus, CPU then puts the data on the data bus, then CPU asserts memory write on the control bus, memory module stores the data and asserts write done. Once more, it's a handshaking, the protocol that the system follows. Let me see what happens in the case of a memory write here. The CPU wants to write something into the memory, then naturally address of that particular memory location into which the data should go, the CPU throws that address. Okay, it may come from anywhere, right? It may come from some registers here. From where this address will come, we'll see when we'll be discussing that addressing modes, etc. That address will be thrown on the address bus. What data the CPU wants the memory to write, that is also thrown into the data bus. That may come from some register or some accumulator into this data buffer. Then it says to the CPU that write, memory write, okay? Either memory read or memory write, one of the signals will be active, right? In this case, the memory write signals will be active. On getting memory write, memory will take that address, will take the data from the data buffer and will write into that memory location, okay, which is being given by the address bus, right? Therefore, this is the 2 ways, right? The handshaking ways. The CPU talks with the memory either to read or to write. Now, in terms of specific control signals, this is in fact just to give you a glimpse that this can take place. These are the different timings, okay, timing states we talk of, say T1, T2, etc., Tk, Tk plus 1, that handshaking signals, naturally ultimately it has to be done through signals, is generated and accepted. So for example, the CPU puts that address bus, okay, activates the address bus at T1. Say this up means the address bus is activated. In the case of a memory read, it asserts the memory read, but memory write is not asserted. On getting that memory read, the data bus, here the memory puts the data on the data bus. There is some delay naturally is involved. The memory has to take some time to put the data on the data bus. Then at the same time, the CPU says the data ready. On getting a data ready, the CPU takes the data from the data bus, say at the time instant Tk plus 1. Okay, this is where the memory read cycle is concerned, right? In the case of a memory write, the signals will be somewhat similar. Okay. You see in the case of a memory write, that CPU sends the address. Okay. Once more, that address bus is activated at CT1. Here the memory write is activated, okay, not the memory read. Data bus, in the CPU sending the data bus is activated immediately as the address bus is thrown. The data bus is also activated. And here, so at this point, memory, after writing the data into the corresponding memory location pointed to by the address bus, the memory asserts, okay, the write done. On getting write done, CPU withdraws all the signals at say tk plus 3 or tk plus 2, all the signals are withdrawn. Okay, that is the way that CPU and the memory will talk with each other, will send or receive information, whether it's instruction or whether it is data. Okay. Now, one important thing that I should also mention here, that we are talking about an accumulator based computer only, right? But naturally, only one register which is being able to participate in arithmetic and logical operations is a very restrictive one. Naturally, all modern machines is not accumulator based. There are many general purpose registers which can participate or take place, that addition, subtraction, multiplication, divisions, etc. These different instructions can take place on many general purpose registers or many registers, not only a single register like accumulator. Now let us come next to what can be there inside the central processing unit. We just give glimpses or parts of the different central processing unit as we are needing. Here I have tried to show, once more I said that an accumulator based a simple machine. Okay. Now here is the external control bus, address bus and data bus that I was talking of. Okay, here you see here is that address bus, a data bus and the control signals that is coming with the time and control are going out of the CPU. Inside, here is an arithmetic and logic unit which does that all arithmetic and logical operations. The arithmetic and logical operations that the arithmetic and logic unit can perform are like say addition, subtraction, multiplication and division. It can be on fixed point data, that means where there is no decimal point, or it can be on floating point data where there is a decimal point. Now the floating point is essentially an approximation of the real numbers that we have, and we will discuss about this floating point number representation as well as a fixed point number representation in our number representation classes, right? But this arithmetic and logic unit, what this arithmetic and logic unit does is that it does all this arithmetic and logical operations. Naturally, I have shown only one arithmetic and logic unit over here, but at least generally there is two arithmetic and logic unit, one for fixed point arithmetic and one for the floating point arithmetic. At least these two kinds of arithmetic and logic units are there, and there can be more than one arithmetic and logic unit of one type, okay, just to performance enhance it. Here we have shown only one, just to have a simplified picture. Here is that accumulator. There are, I have shown several registers here which can hold data within the CPU. That means not always that you will have to get an operand, you will have to go out and fetch the operand from the memory. You can bring, once you bring some operand or once you compute something by means of an arithmetic and logic unit, the intermediate results of the operands can be kept in registers. I have only shown 3, but nowadays any computer have many such registers. It can be 16, 32, 64, 120, 256 like that. Okay. Here is a stack pointer as a special significance, we'll see, and the program counter that I was talking of has a special significance. Okay, I have some or part of it which I have already discussed. Now, here is instruction register where that instruction, when it is fetched, okay, comes through this line into what we call an internal data bus. Therefore, the content of different registers within the central processing unit are generally passed through this internal data bus. So, for example, something coming from the memory through the data bus will be on that internal data bus, and from that internal data bus it will go to the different destination registers. For example, if say instruction, then that instruction after being fetched, it will come through the data bus into that internal bus and will come into the instruction register here. Okay. At this point, it will be decoded, right? On decoding, it will know that which instruction it is. That will now excite that control unit, okay, to generate the signals to the outside world, to the memory, as well as to other devices that is connected to the machine. Also, it will give signals to internally to the arithmetic and logic unit, right? The arithmetic and logic unit may also get an input from the decoder, but if this is not an essential feature, if the decoder comes to the control unit can send all the relevant messages or the signals to the arithmetic and logic unit, right? Similarly, this control unit sends all internal signals to control that which register content will be transferred to which register content. Therefore, all control functions of transmitting informations from register to register inside the central processing unit, or any information that has to be passed from the environment that outside the CPU, may it be memory, may it be IO devices, all this is controlled by the control unit by sending appropriate signals to the different units and to the buses by opening and closing buses. That's a very important subunit of a computer which have to be properly designed, and we'll see, okay, a design of a control unit. Now here we have shown the flags, right? These flags, that the sign flag or zero flag that I have shown, there are some such flags. I should not say too many, but there are some such flags which is I should say state or reset by the arithmetic and logic unit, output of the arithmetic and logic unit, and which also will control. This will be an input to the control unit to decide, right, what control functions are to be generated, control signals are to be generated. You see that here the arithmetic and logic unit output is set to that internal bus, right, to be sent to any of the registers, okay, or to that accumulator or to a temporary registers, right. Now, as I said that there may be many registers which can take part directly into the arithmetic and logical operations. Now, one important thing that I would like to mention is that arithmetic and logic operations that a particular computer can perform is not too many. Okay, for example, addition, subtraction, multiplication, division, then ANDing, ORing, exclusive ORing, and simple decision taking. That's what a computer can do. But real power of the computer does in accurately doing millions of such instructions in 1 second. Okay, that is the speed of the operation and the accuracy of the operations, where in fact which has to be harnessed. Okay, just to get a real benefit out of a computer, right? Now, this is so far as the CPU is concerned. Let us say, apart from that memory, the CPU is also connected to many devices, right? So, for example, here I have shown a disk drive and video display unit, a keyboard, mouse, and memory. All of them are taken to be, so to say, the devices by the CPU, and all of them hang on the bus, right? Now, a particular device, either a disk drive or you say video, it connected to this bus, okay, by means of an what we say that interface and device controller. Though I have shown that interface and device controller in one box, actually this is not in one box that interface that the interface and the device controller are there. That means it split generally into two functional units. One is that interface and the device controller, as I have a little bit elaborated here. Okay, that here you see that the address bus is there, once more the data bus is there, the control bus is there. Here is that interface, okay, IO module interface, okay, or sometimes it is called the port, and here is the device controller. Okay, the device controller controls the device, generates the data, either input or output data as is necessary. It also tells the IO module or that interface module, okay, that whether the data is ready or whether the error signals is there or not. CPU then, through this interface, takes in the data, okay, or puts the data into that output device. Therefore, what I would like to mean here, that a device will talk with the CPU through this IO module or through this interface port. If CPU wants to send something to the output device, it will send through this IO module connected to that output device. And CPU wants to take into something from an input device, then also CPU will talk with, okay, through some protocol with the interface of that input device, right? And as we will see later on, that a device can talk with the CPU through the IO port, okay, in three different ways, right? That IO port will communicate with the CPU in three different ways. One we call that program control mode of data transfer, one we call that interrupt control mode of data transfer, and another we call the DMA. In the case of a program control mode of data transfer, CPU all the time keeps track of what is happening, okay, to the device, that means what device is doing through that interface, right? In the case of interrupt, the CPU tells the device to take an action, and the CPU then does its own job. Device, on completing that action, tells the CPU that my job is over, now you take action. Then the CPU takes that action. Okay, that's called that interrupt control. In this case, CPU time is not wasted on a busy wait. Okay, CPU need not go on all the time checking what the device is doing. Another is, in both the cases, CPU in fact is a master. Now, possibly by this time you are aware, you have become aware, the CPU is a master of the computer. That means it always controls what is happening. That means what data transfer takes place to the bus, everything is controlled by the central processing unit. Right? But in the case of a DMA, that means direct memory access, what the CPU does is that CPU for time being relieves the control of that bus, the mastery on the bus for some time, and that time is taken by a device to transfer some data between itself and the memory. Okay, this is called the direct memory access. That means the device directly accesses memory either for taking some data from the memory or putting down some data into the memory, and to be able to do it, CPU has to relinquish the mastery of the bus for some time on its own on request from a DMA device. Okay, all these modes of data transfers are very important, and all these modes of data transfer we will discuss in detail in course of our lectures. Right now, just one more thing that I should discuss is that in the case of a CPU and memory, you see that for execution of a program, the CPU and the memory turns out to be very important, and the speed of the CPU and memory are very different. In the case of a memory, okay, the memory speed is much lower, and therefore the total memory has been broken down into, so to say, a memory hierarchy. Here is the main memory, okay, here is the CPU registers, Here the CPU is very fast and the main memory is not that fast, and therefore somewhat intermediate speed memory is put, which we call cache, so that generally CPU takes that data or instructions from the cache, okay, which is already loaded into the cache from the main memory. And if the CPU finds that required data or the instructions is not in the cache, then only the CPU comes to the main memory, okay, to get the data or the instruction, and that is loaded into the cache. Okay, therefore basically the cache speeds up the operation or execution of a program. Now similarly, the main memory is limited in size, and we have that magnetic disk at the back, okay, that we can map the informations in the magnetic disk into the main memory. And for archival purposes or for taking that backup, that magnetic tape is used. That means whatever that magnetic disk has, okay, if it is full or temporarily, intermittently, okay, sometimes the content of magnetic disk is now backed up into the magnetic tape. And as you've seen already, that in the case of an optical disk, that it is read mostly, write once, that we use this for archival purposes or for example, say for transferring softwares from system to systems. Okay, that is the situation so far as our memory hierarchy is concerned. The memory can be thought of as if it is a hierarchically placed. Okay, the sizes are different. What this memory hierarchy is, we will discuss in detail when we talk about the memory modules. Right. Now, just one important thing that I would like to say here, that what we had been talking about are the von Neumann machines. Okay, that's the basic model that we'll be working with, but as has been done over the years, many performance enhancing modifications has been done to this von Neumann machine. As I've already told, there may be more than one arithmetic and logic units, okay, so that the speed up is done. In fact, in a system that can be more than one central processing unit, we call it a multi-processing unit. It may be loosely coupled, it may be tightly coupled. Okay, by loosely coupled, I mean that share the informations by means of a shared memory, and loosely coupled, we mean that they communicate between them or amongst them by means of message passing. Right. This performance enhancement has been made, and naturally nowadays the computing systems have started to be very powerful, and you have already are aware of that computer networks, etc. Now, from in our next lecture, we'll first see that what is the role of an operating systems, the overview of its functions. Now, for today, we stop here.